So we're going to show something quite important, which is that if you have a binomial random variable x with success with n trials and success probability p, then you can express this uh, binomial random variable as the sum of n IID Bernoulli p random variables. So IID means independent and identically distributed, and these n IID Bernoulli p random variables have to have the same success probability p. And the Bernoulli random variable, is the random variable that takes 1 with probability p, and then 0 with probability 1 minus p. And to do this, we actually have to, one way to do this is to look at the moment varying function of the binomial random variable and that of the Bernoulli random variable. Okay, so if we want to calculate the moment varying function of the binomial random variable, x, then we have to use the following, which is the binomial theorem. So you've probably seen this in your algebra class, but if you haven't, here's a statement. If you don't need to prove the statement, and in fact, we're not going to do this. You can just look it up on Wikipedia. So for real numbers x and y, x plus y to the n is actually the sum from k equals 0 to n of n choose k. So I write my n choose k like that. You might write it like nck, but here it is, n choose k, x to the k, y to the n minus k power. Now, if we apply the definition of, so the moment varying function, the MGF, the definition is expectation of e to the tx. So this is the MGF of x. Now, if we apply the definition of expectation, you take the function e to the tx, right? So we have e to the tk. K is what values x takes. So x takes values from k equals 0 to n because it's a binomial random variable. And then this part is just the PMF, the probability mass function of the binomial random variable. And to go from this line to the next line, all we do is we have this e to the tk and we have the p to the power k, and then we just factor it into p times e to the t, all to the power k, right? And everything else is the same. Now we can actually apply the binomial theorem. So we have the n choose k, right? And our x here is going to be p times e to the t, and our y here is 1 minus p, right? So you can see all the k's and the n minus k's match up. So our x, like we said, was p times e to the t. Our y here is 1 minus p, right? And you probably will see this version more. So I switched order. 1 minus p, bring it to the front. 1 minus p plus p times e to the t, all to the power n. And that's just the moment varying function of the binomial random variable. So it's actually quite simple to calculate if you know the binomial theorem. Now, we love the MGF because if the MGF exists, then we can actually take the derivative with respect to t of the MGF, right? So we can use the power rule here. So this expression, we use the power rule to bring down the n, and then we have a n minus 1 power of this expression. And then we have to apply the chain rule to take the derivative of this expression here. So these the 1 and the p are constants with respect to t, so they're 0. And the derivative of e to the t is just e to the t, so we have p e to the t. And if you evaluate this at 0, e to the 0 is 1, so we just have 1 minus p plus p. Now the p's cancel out, so this is just 1 to the n minus 1 power, which is just 1. And this is also just 1, so we have n times p. Now, if you take the second derivative of the moment varying function, so all we have to do is take another derivative of the first derivative. Again, it's the same procedure. We have a power rule, so we have n times n minus 1 to the power n minus 2, and then we have to apply the chain rule again. So we already had a p e to the t here, so by applying the chain rule, we're going to have it twice, so we square p times e to the t. And then we have to apply the product rule. So we have to take the derivative of pe to the t, but that's exactly just pe to the t. And here it just remains the same from the product rule. So this is actually just, we get m prime x of t again. So this is the second derivative of the binomial random variable, of the MGF of the binomial random variable. And if we, right, so one thing to comment is that this is equal to the first moment. So this m prime of x at 0 is equal to the first moment, which is why we like the moment turning function. If we set the second derivative of the MGF to 0, evaluate it at 0, then we can, so this is just 1, so we get n times n minus 1, and then this is 1, so we get this p squared, right? And then this is m prime of x of 0, right? And we already calculated that. That's just mp. That's what we get. And then we want to find the variance. So this gives us the second moment. So this gives us e of x squared. We want the variance. And if you apply the definition of the variance, this variance of x is equal to e of x squared minus the quantity of x squared. And this, you know, by definition of the MGF, we found this quantity. And this is also just m prime of x of 0, right? And if we substitute our expressions, right, here, and then here, and if we do some algebra, then we just, this is n squared p squared, right? So this cancels out with this. And all we're left with is np minus np squared, but you're more commonly going to see np times 1 minus p. This is just factorization. Now, remember the original statement that we wanted to prove was this statement, right? That that the binomial random variable is the sum of NIID Bernoulli P random variables, right? And we just got sidetracked with some calculations of this first moment and the second moment. But this is pretty important. You're gonna have to do it for homework, for exams. So now to prove the statement, we want to find now the MGF of the Bernoulli P random variable, right? So let's say we have a Bernoulli P random variable y. So the moment generating function of y is, by definition, the expectation of e to the ty. And the Bernoulli P random variable, the good thing is that it only takes two states. It's either 0 or 1, right? So we have to evaluate, e to the t times 0. So this is 1. And then it takes the state with probably 1 minus p. So it's 0 with probably 1 minus p. And it's 1 with probably p. So this is actually just 1 minus p plus pe to the t. Right, it is kind of familiar from the expression of the MGF of the binomial, right? So that's where we're headed. Right, again, we're going to get, sidetracked a little bit with calculating the moments of the Bernoulli from the MGF. If you just take the derivative, like we did with the binomial, this is just p to the t. You evaluate at 0, you get p. The great thing about the binomial Bernoulli random variable is that once you take the first derivative, all following derivatives of the MGF are the same. It's just p e to the t. So if you evaluate the second moment at 0, if you evaluate the MGF at 0, the second derivative of the MGF at 0, then you get p, right? So this is e of x squared. The nth moment at 0 is e of x to the n. So they're all equal to p, right? And the variance of y, by definition, is e of x squared minus e of x quantity squared, which is p minus p squared, right? So this is, right, this is the first moment, this is the second moment, right? So we have to square the first moment, which is p times 1 minus p, right? So now we want to find the moment generating function of the sum, right? So we want to find the moment generating function of x1 plus all the way up to xn. Now that, just by definition of the MGF, is expectation of e to the t x1 plus xn, x1 plus dot 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 plus xn. And we're just going to distribute the t's, right? So t x1, t of x2 plus t xn, right? And you can just apply this is distributive. Now here we just apply the property of exponentiation, right? So this is exponentiation over here. This becomes a product of e to the txi. And because the xi's are IID, or so because they're independent, we can actually, the expectation of the product, right, x of y is equal to expectation of x, expectation of y, right? So because they're independent, we can actually take this product outside. So this is independence. Now, we already evaluated the MGF of one of them, right? It's 1 minus p plus p e to the t. But they're IID, so they're identically distributed. So the MGF of one of them is the same for all of them, right? So there's no dependence on I over here. We take the product from I equals 1 to n, but they're all the same. So there's no I here in this expression. So this is just 1 minus p plus p e to the t to the nth power. But if you go back up, this is actually just the same thing as the MGF of the binomial random variable, right? So they're the same. So how do we conclude that the statement that we want? So this we don't really show in this class, but you're going to use this statement over and over again. It's that the MGF uniquely determines the distribution. In other words, if x and y are random variables such that the moment varying functions are equal to each other for all values of t, where the MGF exists, then the distribution is the same. So f of x is the distribution function of x, and f of y is the distribution function of x of y. But we have the same values. We need to have the same values of x. So right. So if the MGFs are the same, then the distribution functions are the same, and you're gonna apply this this statement over and over again. So since these two MGFs are the same, we can conclude that x equals x1 plus plus xn. These have the same distribution.